Hello and welcome to another session in physics. In this session we'll be looking at the topic energy quantization. But before that, let's review our previous lesson. Welcome back. Now when we talk about quantization, the first person that comes to our mind is Bohr. From his atomic model, Bohr suggested that the electron in the atom exists in discrete energy levels known as quanta. So therefore we can say that quantization is simply a situation where atoms can move, or electrons can move, in discrete energy levels from energy level 1 say to energy level 2, from level 2 to level 3. Then we have the ground state, which is the minimum or ground level energy where electrons cannot go lower than. Now, energy in such bodies that are being emitted or transmitted in separate or discrete energy packets or energy levels, like we said, is called energy quanta. And this energy quantization, the energy given out by a photon or an electron, is given by h times f, where h is Planck's constant and f is the frequency of the radiation. Okay, let's talk about energy levels in an atom. Of course, we know that electrons in an atom are arranged around their nuclei position, known as energy levels or electron shells. Now, in the structure of an atom, the nucleus, of course, is the center. In the nucleus we have protons, positive charges, and then of course in the nucleus we have neutrons as well. And then we have our electrons. Electrons are negative charges. Electrons, we have them, so many of them, negative charges, and they are at the outer shell known as the electron shell. Now, it requires more energy to remove electrons from the first energy level than it requires to remove electrons from any other higher energy level. So the energy of an electron is given by this relation, minus 1r over n squared. Now let's talk about what n means. N means electron quantum number, r is a constant. The minus sign signifies that work must be done on the electron in order to remove it from the atom. Let's talk about energy states now. The ground state is the stable state, or an atom corresponding to its minimum energy. The ground state is the stable state of an atom corresponding to its minimum energy. So when an atom is heated with an energetic particle, the atom becomes excited. It becomes happy, so to say. When we say the atom is excited, it means the atom is now in a state of higher energy level where the atom becomes unstable. 1 electron volt, known as 1 eV, simply refers to the energy acquired by an electron in falling freely through a potential difference of 1 volt. And this potential difference of 1 volt is given as 1.6 times 10 raised to the power minus 19 joules. Raised to the power minus 19 joules. That is the value of 1 electron volt. Now, during the excitation of this atom, where it becomes unstable as a result of a higher energy level from lower energy level, the potential energy is converted into kinetic energy so that the electrons eventually will acquire a velocity that is given by half mv squared. So the electron volt energy is as a result of this electron that has become excited. Because it is excited, it is jubilating, it is jumping up, it possesses a state of higher energy at this point, and it begins to fall freely through a potential volt of 1.6 times 10 raised to the power minus 19 joules. So what this means is that these electrons that were possessing potential energy and were stagnant at this point possess kinetic energy. Now the energy that is gained by an electron is given as the charge of that electron times the potential difference, which gives us the electron volt. So therefore the electron moves from one level to another level according to this equation. energy level in infinity state minus energy level in the ground state. H is Planck's constant, F is frequency, and it's also equal to H times C, Planck's constant times velocity of electromagnetic spectrum or speed of light, which is 3.0 times 10 raised to the power 8 meters per second. That is the value of C. And then we have this as our wavelength, which is lambda as our wavelength. And then we have this electron volt. So using any of these relations, we can use it to calculate the movement or energy possessed by an electron as it moves from one level to another level. Now let's look at this question. It says the change in energy level of an electron in an atom is 6.2 times 10 raised to the power minus 21 joules. So we're asked to calculate the frequency of the photon and the wavelength itself, and we're asked to take velocity or speed of light as 3.0 times 10 raised to the power 8 meters per second and Planck's constant as 6.625 times 10 raised to the power minus 34 joules second. So let's start with the first one, which is the frequency. Now for us to find the frequency, first of all, we need to look at the change in energy levels, which is given by En minus Eo, where En is the energy in the infinity level and Eo is energy in the ground state level. And they told us that this energy level, everything is given by 6.2 times 10 raised to the power minus 21, as you can see from the question here. Also note that change in energy level is given by Hf, which is Planck's constant times the frequency. So making F the subject of the relation, we can have change in energy over H this time around. So that's why we now have 6.2 times 10 raised to the power minus 21 all over 6.625, which is Planck's constant, as you can see here, times 10 raised to the power minus 34. At the end of the day, we're going to have our answer as 9.358 times 10 raised to the power 2 hertz, which means F equal to approximately 9.4 times 10 raised to the power 2 hertz. In physics, it's always good to leave our answers in standard form. This is the A part of the question. Now let's look at the B part of the question. The B part of the question says we should find our wavelength, which is this. So we need to know that from C, where we have frequency, C is the speed of light, and it's given by frequency times wavelength. We need to make wavelength the subject of the equation. So therefore, wavelength is equal to speed of light over F. And what is our speed of light? 3.0 times 10 raised to the power 8, and our frequency, like we found here, is 9.4 times 10 raised to the power 12. Now when you divide two of them together, you're going to have your wavelength as 0.319 times 10 raised to the power, what we have here, we have 8, and then when 12 goes up, it becomes minus 12. So writing this in standard form, we're going to have 3.2 approximately times 10 raised to the power. Since we have 8 already, minus 12, and then this decimal point moved one place to the right, it becomes minus 1 again. So we're going to have 3.2 times 10 raised to the power minus 5 meters. That's it for this question. Now let's look at another question as well. It says the ground state of hydrogen is minus 26.3 electron volts and the second state is minus 10.3 electron volts, and we're asked to calculate the wavelength of the radiation if the electron returns to the ground state. If the electron returns to the ground state. So as usual, we find our solution. So we need to get the change in energy level, which is given by energy level 2 minus the ground state, which is minus 10.3 electron volts minus 26.3 electron volts. So everything here, change in energy, is going to give us 16 electron volts or plus 16 electron volts. Meanwhile, we know that 1 electron volt is equal to 1.6 times 10 raised to the power minus 19 joules. Therefore, our 16 electron volts is equal to 16 times 1 0.6 times 10 raised to the power minus 19 joules. Therefore, our change in E is equal to HF, which is equal to HC over lambda. So therefore, we have our HC over change in E, which is going to be given as 6.625 times 10 raised to the power minus 34 times 3.0 times 10 raised to the power 8, all divided by 16 times 1.6 times 10 raised to the power minus 19 is going to be equal to 1.9875 times 10 raised to the power minus 25, all divided by 25.6 times 10 raised to the power minus 18. Alright, so if you calculate everything together, our wavelength is going to become 7.76 times 10 raised to the power minus 19 meters. And that's it for this question 2. Now let's talk about line spectra from hot bodies, line and absorption spectra. Line spectra from hot bodies simply refers to what happens to an excited gas when it is examined in a spectrometer. We see that an emission spectrum is seen as a result of the light from the excited gas. And we have a gas like neon, which produces a line spectrum. This spectrum is consisting of a number of well-defined lines, each having a particular wavelength and frequency. Absorption spectra, on the other hand, are dark lines in the emission spectrum of a heated substance due to the absorption of radiation. Electrons are able to absorb radiation if they can jump from lower energy levels to higher energy levels. Now let's talk about the spectra of a discharge lamp. As you can see from the diagram below, if a gas is put into a discharge tube and if its pressure is progressively reduced using a power pump as shown below, we notice that electric discharge will take place in the tube and the gas will glow. The gas glows because its atom is given energy by the flow of electricity through the tube, and the color of the gas depends on the nature of the gas used. Thank you so very much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.